Okay, thanks very much to the organizers for the invitation and for organizing a really interesting conference. So melting in super-Earths. Why should we think about melting in super-Earths? After all, I can think of a lot of reasons why we shouldn't think about melting in super-Earths. We've just discovered them. They're only dots in the sky that dim the starlight a little bit. We know very little about them. And in fact, I don't know of any observations today that can tell us anything about whether super-Earths are melting or not. However, there have been proposed missions, and there is a mission going up in a few years, the James Webb Space Telescope, which should in principle be able to give us some observational constraints on some aspects of melting processes in super-Earths. I think two other reasons for thinking about melting in super-Earths is that melting processes, and I'll be thinking about silicate melting and iron melting both, are a very powerful probe of interior state. So if we want to think about the origin and evolution of super-Earths, then detection of melting processes will be very important. I think a final reason for thinking about melting in super-Earths is that melting may be important for understanding whether super-Earths are habitable or not, and it's certainly been suggested that there is a very direct link. To start thinking about some of these issues, so here's an artist's conception of one super-Earth. Of course, they are just dots in the sky. We can't do cartography of them yet. There has been a bit of cartography of very large exoplanets, super Jupiters and things, but not for relatively smaller super-Earth-sized object. This particular super-Earth is about 5 times the mass of Earth, and what you see here is in the artist's imagination. And to think about some of the choices that the artist has made here, we can compare it, his picture, his drawing, to the surface of Mercury. And one of the things that you notice right away is that while Mercury is very heavily cratered, the artist has chosen not to put any craters at all on the surface of his planet. And what that indicates is that he's thinking of this planet as very geologically active. Now, one of the things we've learned from the space age is that none of the terrestrial planets are completely dead. They're all active. Mercury has a magnetic field. There might even be volcanism and so on. But it has been suggested that this kind of level of geological activity that would erase all trace of craters, or at least to the extent that they're erased on Earth, may be important for the ability to sustain life. And indeed, he's drawn a very, hopefully, this greenish color here to indicate the possibility, anyway, that some of these super-Earths are indeed habitable. Well, let's turn to what we do know about super-Earths today. And this is a plot that we've seen before in a previous talk. This is radius versus mass scaled to the Earth's parameters. And you can see the relatively small number of super-Earths that we have today so far, for which we know both the mass and the radius. Okay, so Kepler measures just radius. There are a few other missions that measure mass and so on. For a few of these super-Earths, we know both mass and radius, which is really the starting point for being able to say anything at all about interior composition. And I've compared, each dot then represents one exoplanet, and I've compared, as the previous speaker did, to the equation of state that you would find, the mass-radius relationship you would find for a pure MGSO3 planet here and a pure iron planet here. You can see that these curves don't quite follow constant density contours, which are in the gray lines here, and that's because of gravitational self-compression. As the planet gets larger, it gravitationally self-compresses, and so the density increases a bit faster, and the mean density of the planet increases with size. This has been expressed in terms of a parameter that I'll make use of in some subsequent equations, this beta parameter, which is a bit less than 1/3, again, just expressing this notion that the density increases with planetary size. The other bit of information that I've added onto this graph is the surface temperature of the planet. Now that's something we can estimate just by assuming a thermal equilibrium with the starlight. This is the equation here. It's relatively simple. This is the temperature of the star, the radius of the star, the orbital distance. Two things we have to assume something about: the albedo of the planet, I'll come back to that in a minute, and also this distribution factor. Okay, if the planet is tidally locked to the star, then all the starlight is hitting one side, and D is equal to 2, it turns out. Whereas if the heat is redistributed by some process, or if the planet is rotating, then D will be 4. I've taken the conservative assumption that D is 4, and I've assumed that the albedo is essentially 0 or small, which is consistent with the limited number of observations that we have so far. Anyway, if you do that, what you find is a reflection in part of observational bias of exoplanets so far. Most of the ones found so far tend to be very close to their star. It's easier to see them there. Okay, and so you get these very high temperatures. We're comparing to the H2O critical point here and to the silicate solidus, and you see several of these circles approaching these sort of green, yellow, and even red, exceeding the silicate solidus type temperatures. So for these in the sort of, for Earth-like compositions, those between a silicate composition and an iron-like composition, here are solar system planets here, you do get a few that are quite hot, and this one I think is one super-Earth where we can be pretty certain that it is molten. And one of the interesting things about that very high surface temperature is that if it's molten at the surface, it's probably molten at depth as well. And this is a calculation that I did in the terrestrial context, thinking about the Earth's magma ocean, and this is temperature versus pressure, and this is the silicate melting interval, or our estimate of it, partly based on ab initio calculations, which I'll say more about in a minute. And this is our calculation, again, based on ab initio, of the isentropic temperature gradient in a molten silicate planet. And I've also indicated here the depth in this particular planet, Kepler 10b, which has this very high surface temperature, more than 2,000 Kelvin. So it may be molten all the way through, actually. Now that's a very different situation from the early Earth. It's a very different situation from the habitable zone, which I'll be focusing on, because the heat in this case comes directly from the star and the fact that the planet is so close to the star. So for the rest of the time, I'll focus on super-Earths, Earth-like super-Earths, that is Earth-like compositions, in the habitable zone. There are a large number of these now that Kepler in particular has found. A few of these we also know the mass of, and so we can start to get at their mean density. And the point, of course, is that in the habitable zone, starlight is very weak, and it's not a significant source of interior heat anyway. Just a reminder of what we can observe, and this kind of leads into the next point about the possibility of observing melting. This was shown before in the form of a movie, and the observations you make are the brightness of the star. Okay, so you look at the brightness of the star, and as the planet transits in front of it, you get a dip in the brightness of the star because of the passing planet. As the planet exits the star, then the brightness comes back. As the planet goes around this way, you get a little bit of reflected starlight, and so the brightness of the star-planet system increases a bit. This tells you about the albedo of the planet. Then you get a secondary eclipse as that reflected light from the planet vanishes here, and so on. Okay, now, why can't we say anything about melting in super-Earths today? Because we have to go beyond this kind of information. And one way to go beyond this kind of information is to start thinking not only about just the integrated brightness, but about doing spectroscopy. And this has actually been done on giant exoplanets already. Hasn't been done on super-Earths yet, as far as I know, but the principle is well understood. And as I said, there are proposed and soon-to-be launch missions that should be able to do this. So if you look at these light curves, as they're called, in different frequency ranges, you can start to constrain the composition of the super-Earth atmosphere because the starlight is passing through it. By the same token, as you're looking at reflected light of the star off the planet, you can see the thermal emission spectra in the infrared as well. That's crucial. You need to do this in the infrared. And this then gives you the potential for detecting silicate melting. One of the consequences of silicate melting is alteration of atmospheric composition, and there might be a few key molecules that you might want to look for, perhaps water, perhaps sulfur dioxide. It's certainly been suggested in the context of Venus here. This is Venus Express data and Magellan data here, that sulfur dioxide being large and decaying and then coming back again in the subsequent Venus Express measurement may be due to ongoing volcanism. That's certainly one explanation of these observations. These are observations of an exoplanet. This is a giant exoplanet, and the observations here compared to a very sophisticated set of molecular line lists, and the conclusion of this study was that there is H2O in this particular giant exoplanet. And there are more data than this, but the sensitivity for detecting super-Earth atmospheres isn't quite there yet, but I think it soon will be. The other kind of melting I'll be talking about is iron melting. Why? Because it produces magnetic fields. Magnetic fields have also been suggested as being important to life because they may protect atmospheres from erosion by stellar winds. And what can we say observationally about super-Earth magnetic fields? Well, people have suggested that you might be able to observe exoplanet magnetic fields. Here's one suggestion for how you might be able to do it, whereas a sort of bare planet, if you will, would have a symmetric light curve like this as it passes in front of the star. A planet with a significant magnetic field on it will be preceded by a bow shock through the solar wind, and that will produce an asymmetric light curve. So with higher precision on the measurement of stellar brightness and maybe characterizing the variability of the star a little bit better, you might even be able to detect an exoplanet magnetic field. There may be other ways to do it as well. Okay, so let's think about melting of super-Earths. Let's think about whether it's plausible or not. There have been various claims in the literature whether this is plausible or not. I'll go through an argument based on better characterization of material properties. In the end, it'll still be speculative, but I think we'll learn something in the process, and we can say something about whether melting is plausible or not. Okay, so where's the heat coming from to melt a super-Earth? Well, just radioactive heating probably isn't enough, not for an old planet anyway, and so you probably need an additional heat source. And planets probably do have an additional heat source buried in them from their formation. We think the Earth does, certainly, probably the other terrestrial planets do as well. And so what I've done here is to repeat a classical calculation by Tonks and Meloche, but applying it to a variety of different planetary masses, whereas they just applied it to Earth, and they were thinking mostly about the sort of canonical moon-forming impact. So what I've done here is so this indicates the sort of final planetary temperature as a function of its surface temperature, and the planetary mass and the mass of the impactor here, m sub I, and this is a heat capacity that includes the effect of latent heat and so on. So what's going on here? This is just the escape velocity. The impact velocity grows the planetary mass because the escape velocity increases, so impacts hit with higher velocity. So that helps increase the temperature. The other thing that helps to increase the temperature is this factor here. So the larger the fraction of the impactor mass to the target mass, the more efficiently heat is deposited. And this is something that sort of came late in the study of accretion of planets. People thought initially in the 60s and 70s about sort of incremental or infinitesimal accretion. But if you start accreting with larger objects, then you can really bury the kinetic energy quite deep. The scalings here are not schematic. This is based on hydrodynamic simulations from other papers from J. Meloche's group, which match sort of observed crater densities and properties on Earth. Anyway, what are the results? So the solid curves correspond to a sort of canonical moon-forming impact of 10% the mass of the target. And the dashed lines here come from a more modern sort of reconsideration of the moon-forming impact, which prefers larger impactors, maybe 40% the mass of the target. Anyway, it's for sort of Earth-sized planets already. You're melting 50 to 60% of the planet if you start at the solidus temperature, which are the red curves, which I think is quite plausible. So that exceeds the mass of the mantle right there for a single impact. And if you have a 40% impactor, then you melt the entire planet for planets as small as the Earth. And certainly for super-Earths, complete melting is even more likely. So lots of heat to go around in the formation of these planets, probably. Giant impacts seem to be a generic property of accretion scenarios, and they showed up very nicely in Dan Frost's talk, where there's sort of sudden jumps in planetary mass due to giant impactors, 10, 20% I saw in some of his figures being pretty typical. There's an additional heat source that also showed up in Dan's talk, and that is the gravitational energy released by core formation. So what Yannick Ricard and his group are looking at here is a relatively small planet, actually. This is sort of moon-sized, or maybe even smaller. I don't remember exactly, but quite small. And they've brought in sort of a preformed core, and this core sinks very rapidly to the bottom. And as it sinks, it creates all this heating of the planet. And this is release of gravitational energy. There's less gravitational potential energy to have the heavy stuff on the bottom than it is to have the heavy stuff on top. And this actually scales with planetary mass like this, like the mass divided by the radius. And so even for Earth-sized planets, you're getting substantial heating. And for sort of a 5 Earth mass planet, then this can be a very large amount of heating indeed. Okay, so it seems plausible at least that many super-Earths will start out in this completely molten state. And indeed, there's a good chance that the Earth started out in a completely molten state. And the question is, what happens next? How do we get from this very hot initial state with plenty of energy deposited in the interior to something more more solidified, sort of 4 billion years later? Okay. Well, for that, we need to learn something about material properties. There are a lot of processes that are going to be going on. There's the dynamics of this magma ocean, which will cool the planet. What are those dynamics like? There is crystallization. What is the melting temperature? There's crystal liquid fractionation. I won't be getting into that, but that depends on the density contrast between liquid and crystal, and so on. So we need to learn a bit more about material properties at sort of super-Earth conditions. This is challenging for us because I give you the pressure scale for the Earth here, but pressure scales approximately with planetary mass. So for a 5 Earth mass planet, you're talking about pressures well beyond those in the center of the Earth, and for a 10 Earth mass planet, quite large pressures indeed. And we don't have a lot of experimental data in that regime. And so we have to think about other approaches, at least for now, and new experiments and new kinds of theoretical calculations as well. And this is just to say that one of the things we've learned by starting to examine this pressure regime is that there's surprisingly rich phenomena at these very high pressures. One of the things that happens, this is the phase diagram of iron up to 1 gigabar. So this is the center of the Earth is 3 megabars, and this is 300 times that. This is partly to look at super Jupiters, but also we have sort of center of super-Earth type pressures here as well. One of the things that's interesting is that it's almost like the alchemy that Dario Alfei was talking about before, because if you think about transition metals, you know the valence electrons are in the 3D shell, right? And the 3p electrons have a much lower energy. They're very tightly bound to the nucleus. They're core electrons. They don't participate in bonding. But as you go up in pressure, actually, the atoms get so close together that these core electrons start interacting with each other. And these are the 3p states here. They start to broaden, which is a measure of that interaction between neighboring atoms, and they start to overlap with the 3d electrons here. And that stabilizes these new solid phases of iron out here. These kinds of calculations are testable by new class of experiments, laser-induced shock. There's a nice poster on this process here, actually. And this is very exciting, in principle capable of following this sort of temperature pressure path here and testing these predictions, which have important implications for what we think super-Earths might do. So Dario showed a movie, and I'm not sure this is going to work. Oh, there we go. Okay. So just to illustrate some of the things some of the properties I'll be talking about. This is starting with crystal on this side and liquid on this side. This is a magnesium silicate composition. Some of the things I'll be looking at are the average vibrational amplitude of the atoms in the crystal. That's a proxy for melting temperatures at very high pressure. Melting temperatures themselves, which you can also get at by this sort of two-phase coexistence, just letting it go until one of the two wins, the crystal or the liquid. And you can see the liquid winning here. The crystal is melting. And the other thing we can get at is the viscosity, which is related to how fast these atoms are moving. As Dario also mentioned, all the physics in that simulation, aside from Newton's equations of motion, comes from how we calculate the forces. And the forces are calculated with the density functional theory. Dario gave a nice introduction to that. just backing up a bit from that introduction, the reason we use density functional theory is that it does have predictive power, no free parameters, no a priori assumptions about the shape of the charge density or nature of bonding, which is really important in this regime where we don't know what's going to happen because we haven't been to these pressures before. Scope, entire pressure, temperature range of planets, and even stars. In principle, there's no limitation there. Entire periodic table. And it turns out that they're quite accurate. This is just a comparison between calculation in the lines and measurements in the symbols of shock wave compression of two silicate liquids. Okay, so we can measure the viscosity by the same methods that Dario talked about, looking at the decay of the shear stress autocorrelation function, and we can calculate the viscosity of silicate liquids, of the magma ocean, if you will, the silicate magma ocean as a function of pressure. We focused on the terrestrial regime here, but we don't expect huge variations, even up to super-Earth conditions. We expect the viscosity over the Earth. It increases by like a factor of 10 or so, and it might increase by another factor of 10 in the super-Earth. But the point is that the viscosity remains really quite low, and much lower than sort of that controlling solid-state mantle convection. And so magma ocean dynamics are going to be very different from solid-state mantle convection. In this sort of regime diagram, again after Tonks and Meloche, we've got solid-state mantle convection here at essentially infinite Prandtl number and pretty high Rayleigh number. Here's the magma ocean up here. Now, if the viscosity is 20 orders of magnitude less, then the Rayleigh number is going to be 20 orders of magnitude greater, right? And there it is. Also pretty low Prandtl number. This is the highest Rayleigh number experiment, fluid dynamics experiment that I know of. So this is a sort of unexplored regime. There are scaling arguments out there in the literature that allow you to estimate things like heat flux in this regime. It does depend on Prandtl number in this regime. And you get really extremely large heat fluxes, exceeding the heat flux incoming from the sun. So a very different sort of surface boundary condition for the magma ocean. What else can we say about the relevant material properties? We can estimate melting temperatures. So here's temperature versus pressure for silicate melting, and this is our estimate of the liquidus and the solidus compared to a variety of ab initio and experimental measurements and calculations here. There are good arguments, and I'd be happy to go into these, why this ab initio calculation is likely an upper bound. This is a proposed liquid-liquid transition from a laser-induced shock experiment, so that's, again, an upper bound on the melting interval. And this is calculated with that Lindemann law based on the vibrational amplitude in the crystal. We're doing a little bit better here thanks to the calculations of Morard et al. For iron melting. They did that two-phase molecular dynamics type simulation to see whether crystal or liquid would win under a variety of pressure temperature conditions. And I think we have a pretty good handle, actually, on the melting temperature of iron up to at least up to the pressures characteristic of the center of a 10 Earth mass super-Earth. We combine this also with a thermodynamic model known as Hephaesto. Be glad to say more about that later, which allows us to calculate the planetary structure and isentropic temperature profiles. Okay, so what can we do with this? Now comes a bit of speculation. How can we put these together to evaluate whether melting in super-Earths is likely and whether magnetic field generation in super-Earths is likely? And it's the magnetic fields that I'll really focus on here, following on from some of the things that Bruce talked about. So if we look at the cooling time scale as a function of temperature, this is at a typical pressure of 1 megabar in a super-Earth, say, and we start with at super liquidus temperatures with a very rapid time scale of maybe 1,000 years for cooling, but this cooling time scale increases very, very rapidly as we start to crystallize. The shape of this is partly based on experimental information, and then as we get to a crystal-dominated region with some partial melt, we get a different trend, which is also constrained experimentally, and the cooling time scale then depends very strongly on the liquid fraction, which is phi here. The exponent here is like 26. And then finally we get into the familiar sort of subsolidus regime here. Okay, so what I'll argue is that this interval between solidus and liquidus is really important for controlling the time scale of cooling. And I'm going back to a very old idea of Tozer's and adding one twist to it, which is the idea of thermal regulation. So the idea is as you cool the planet, you'll start to freeze a little bit of that partial melt. That'll increase the viscosity. That'll then decrease the heat flux, which will warm the planet and induce a little bit of melting. So the idea is that for a long time, you might stay in between the solidus and the liquidus in a sort of planetary thermal evolution scenario. Now, one of the things we know about crystallization is that it's very unlikely to be homogeneous. Okay, we're not going to be, the temperature of the liquidus and solidus is not going to be the same everywhere. The cooling isentrope is not going to intersect liquidus and solidus uniformly as a function of pressure. So we have to think about inhomogeneous distribution of melt. And here's one way I've thought about it. I don't know if it's right or not, but we start with the melting interval here is indicated in green, and the planetary temperature profile is indicated in red in all these cases. Okay, so you start with a superliquidus magma ocean. The adiabat is steeper than the melting interval. As you cool, the planetary temperature falls in between liquidus and solidus. And it's likely to parallel liquidus and solidus in this regime because it's so strongly controlled by the latent heat of melting. Now, what happens next? How do you get from here to here? I don't know. One of the things you can say is that the temperature contrast across the thermal boundary layers is likely to increase. This is a simple scaling argument, which indicates that the temperature contrast goes like the viscosity to the 1/4 power. Even though it's only the 1/4 power, we're talking about a 20 order of magnitude change in viscosity, right? So this is going to produce a significant change in temperature contrast. Another way to think about it is that the mantle may want to hold on to a little bit of melt to increase the efficiency of heat transport. And the most likely places to do that, just because of the relative slopes of subsolidus isentrope and melting interval, are in the thermal boundary layers at the base and near the surface. Does this make sense at all? Well, we do have one point of comparison, and that's the Earth. And the Earth does seem to have this kind of temperature profile. It does certainly have partial melting at the surface, and it seems to have partial melting at the base as well. This is a cartoon of ultra-low velocities, so-called ultra-low velocity zones, which may be partially molten regions at the very base of the mantle. Okay, so we can put this all together, and what I've done here is to plot our silicate melting interval from partly ab initio calculations and our core melting interval, mostly from ab initio calculations from Morard et al., for a super-Earth and for an Earth-type pressure regime here. Okay? I've also indicated a temperature profile. In the super-Earth, this is just an adiabat. Okay? I think that's pretty uncontroversial. I've assumed that the potential temperature is set by silicate melting at the surface. Okay? So that fixes the adiabat. And I've assumed that the base of the mantle is partially molten, and so that fixes this point on the adiabat here, on the planet, on the super geotherm here as well. And then the core again is, I've assumed, is adiabatic. Okay, so by assuming that the temperature at the base of the mantle is fixed by the silicate solidus, you end up producing this relatively large temperature contrast, which means lots of heat coming out of the core, which means plausible magnetic fields. I'll get back to that in a second. One point to make is that there are a couple of mantle convection simulations of super-Earths here from Paul Tackley and from David Ewan's group here. And people have looked at these before and said, well, this isn't plausible. These large temperature contrasts aren't plausible because, look, here's a simulation that has no temperature contrast, a relatively small one. The point is that these basal temperature contrasts in these simulations are assumed. This is a boundary condition, right? They don't come out of the calculation, they're put into the calculation. And what I'm suggesting is that it may be more plausible to investigate dynamics in this larger basal boundary layer regime instead. Okay, so Bruce already talked about the importance of getting heat out of the core. I've just relied on this very simple comparison to evaluate the plausibility of super-Earth magnetic fields. I can look at the heat flux coming out of the core by looking at how that temperature contrast scales with planetary mass, and it ends up going linearly with planetary mass. and I can also look at the conductivity, taking into account Darya's value of the conductivity and how it depends on pressure, and so on, and it increases more slowly with planetary mass. You can see for an Earth mass, these values are similar, consistent with what Bruce was saying. For smaller planets, you might fall below. Conductive heat flux might actually be greater than the heat flux coming out of the core. But for large planets, this is likely to exceed. At least it doesn't seem implausible for super-Earths to have magnetic fields based on these arguments. And I'll leave the conclusions up. Thank you.